Hello everyone, this is Homer White, back again, now for part 1 of the 6th chapter of our course on the design of studies. So in this part, we're going to talk about observational studies, and we're going to look at the idea of causation, and wonder whether you can infer much about causation from associations between variables that you might discover in the course of an observational study. One of the primary obstacles to inferring causation in observational studies is the possible presence of confounding variables that end up doing some of the causal work in addition to, or perhaps instead of, the explanatory variables that you actually had in mind. We'll also look, in an introductory way, at the idea of experiments. These are a slightly different type of study that are aimed again to examine relationships between two variables, but to be a little bit better at detecting causation when it exists. Always make sure to remember that you've loaded the necessary packages. So, observational studies. The really interesting questions in science are about relationships between variables. Usually one variable x is considered to be an explanatory variable, and the other variable y is considered a response. This is only a distinction that we make in our minds. It's provisional, and it's also not useful in many studies. But in the kinds of studies that we have in mind here, this distinction is going to be in play. So the explanatory variable might help explain the values of the response variable. It might help to predict them, or, and this is what we'll be most interested in this part of the course, we think it might help to cause the values of the response variable y. So let's look at an example, the relationship question, does smoking cause lung cancer? Now smoking is an activity, and lung cancer is a condition. But in order to examine this question from a statistical point of view, we introduce variables that are related to the activity and the conditions in question. We look at the variable smoke, which could be measured on an individual. Any individual could smoke, yes, or not smoke, no. So there's a factor variable that you could measure on individuals. And that's going to be the explanatory variable in this study. The response variable is another factor variable, lung cancer, with values yes or no. Yes if a person has lung cancer, no if the person does not. So we can interpret, does smoking cause lung cancer, as a question about the relationship between the variables smoke and lung cancer. And in particular, we're wondering if the variable smoke plays a causal role in determining the values of the variable lung cancer. Now, for some more examples that pertain to observational studies, we also want to look at a sample data frame, this one from the TigerStats package. So if you have not done so already with the data frame attitudes, you should probably learn more about it. Remember that we do this by first getting a close look at the data frame. First, we make sure that the data frame is put into our global environment using the function data. And then we can use the special RStudio function view to view it in a files pane and see the variables present along the columns, the individuals along the rows. And we can learn more about the data frame. We can read it in context, as it were, by getting help on it and learning who collected the data and for what purposes. When we ask for help, we find that this data frame is the result of a survey that was carried out at Georgetown College in the fall semester of the year 2001 by some students in a Math 111 class. These students surveyed 267 of their fellow students in a variety of classes all on one morning in the fall of 2001. Every subject in the study was given a survey form containing several questions on it. One question that we'll examine at more length in just a bit was a hypothetical question where the subject was asked to imagine that they were on a jury where a defendant had been convicted of a certain crime, and in this state jurors were allowed to recommend sentences to the judge. And they were asked to look at the details of this crime and to recommend a sentence. They were also asked a separate question what major they planned to pursue at Georgetown. And based on their answers, the students grouped their majors into 4 groups: math science majors, humanities majors, social science majors, and pre-professional majors. So the research question that's suggested just by those 2 variables that were measured might be this: who gives the longest sentences on average? Math science majors, humanities majors, social science majors, or pre-professional majors? Here it seems most useful to think of the explanatory variable x as major, a factor variable having the 4 values that go with the 4 classes of majors indicated in the question. And we can think of the response variable as sentence, the sentence recommended. It was given in years. Let's take a quick look, just because we're curious, at how things came out from a descriptive point of view. First, looking at it numerically, we could ask for phase stats on sentence broken down by major in the attitudes data frame, and you see here a portion of the output. Remember, what we're looking at when we're looking at the relationship between 2 variables is the conditional distribution of one of the variables given the possible values of the other variable. So the output you see before you gives you a certain amount of information about the conditional distribution of sentence given each of the 4 possible values of major. And since means and medians are included, you could do such things as compare the centers of these conditional distributions. And whether you compare the medians or the means, you see that the conditional distribution for sentence, given that major is math and science, seems to have a higher center than the other 3 conditional distributions. For example, just to back it up specifically, on average, looking at the means, math science majors sentenced the convicted defendant to about 30 years, whereas the other majors sentenced the convicted defendant to about 15 years. This difference in the centers indicates some relationship between the variables. If you want to look at it graphically, with the combination violin and box plots, you see the difference again. And in particular, you notice that the math majors are up around 30 years for the median. Pre-professional and social science majors are around 25 years for their median. And humanities majors have the lowest median at 20 years. Now I bring up the research question that we just examined because it's an example of a certain kind of study, an observational study. Now in an observational study, this is the definition of the term, researchers simply observe or question the subjects. In particular, they measure the values of the explanatory variable x, and they measure the values of the response variable y for each subject. And that's all they do. They measure those values. They don't interfere, or at least they interfere as little as possible, in the lives and the activities of these subjects. They only interfere to the extent needed to actually measure those variables. Now, I did mention that one of the reasons that we like to study the relationship between 2 variables is because quite often we're interested in the causal question. We're interested in whether one variable causes the values of the other. So we want to pull back and examine the issue of causation in a little bit more detail, and then we'll begin to wonder whether causation can be reliably inferred just on the basis of observational studies. So, thinking about questions where you're wondering if one variable causes the other, here's one where we're pretty sure of the answer. I think most of us would think that speeding causes tickets. Now, diagrammatically, we'll represent each of the variables involved with a little ellipse. So we have the explanatory variable speed, which I assume is some numerical variable, the speed you're traveling, perhaps measured in miles per hour, and a response variable, ticket, which is a factor variable. Yes, you get a ticket. No, you don't. Now, our belief that speeding causes tickets is represented diagrammatically here with an arrow from speed to ticket. So a pointed arrow indicates a causal relationship. Now, I want to further refine our notion of causation. I want to make it really clear that a cause can be a partial cause of some other variable. It doesn't have to be the whole cause in order to be accounted as a cause. So, for example, we know that just your speed alone doesn't guarantee you a ticket. Just because you go 70 miles per hour doesn't mean you're going to get a ticket, even though you might be speeding. Some other things have to happen too. For example, the cop has to see you. And there are other possible factors that aren't even mentioned in the picture. For example, 70 miles per hour on, let us say, the Mountain Parkway wouldn't get you a ticket because you're not even speeding, but 70 miles per hour going down Main Street in a small town would certainly give you a higher likelihood of getting a ticket. So there's a lot of other factors besides speed that go into determining whether you have a ticket, and yet we account speed as causing ticket because it's part of what causes ticket. I'd also like to point out that a cause can be an indirect cause. So, for example, your pressure that you exert on the accelerator is what causes your speed to be what it is. And your speed, in turn, helps to cause whether or not you get a ticket. So indirectly, you're getting a ticket is caused by the accelerator pressure. Even though that's indirect, we still would say that accelerator pressure causes ticket. It just does it indirectly, or less directly anyway, than speed does. All the indirect causes are allowed to count as causes. Now, philosophers have debated for a long time what it means or what it is for one thing to cause another, and they really haven't come to any agreement. So I don't suggest that the rather rough idea of causation that I'm going to present to you in just a moment really is adequate or would hold up under careful examination. But operationally, and for scientific purposes, it seems to work pretty well. So roughly, we say that x causes y if there exist two different values, say x1 and x2, of the explanatory variable x, which are such that whenever two people A and B are alike in every way, except that A's value of x is x1 and B's value of x is x2, then the distribution of the response variable y for A is different from the distribution of the response variable y for B. That's a mouthful, so let's pull an example out of it. For example, we say that speed causes tickets. Why? Because we tend to believe that if you could look at two people who were alike in every way somehow, except that one of them drives faster than the other, then the one who drives faster has a greater chance of getting a ticket. So you see two different speeds, and we imagine two different people who drive the different speeds, but that difference in speeds is the only thing that's different about the people. And we believe in that situation. Not that the person who drives faster definitely will get a ticket, and the one who drives slower definitely will not. But we think there's kind of a distribution in play, that the chances, the percent chance of the faster one getting a ticket is larger than the percent chance for the slower one to get a ticket. And so that's the difference in the distribution of ticket for each of the two people that seems to go along with that difference in their speed. Now, I'd also like to make it clear that there's a distinction between one variable causing the other and two variables simply being associated or related. We've done a lot with detecting and describing relationships, but I want to make very clear that relationship or association isn't really exactly the same thing as causation. It is true that whenever one variable causes another, you'll find that the two variables are associated. So speeding causes tickets. And as a result of that, we see an association. The distribution of chances for getting a ticket is different when your speed is high than it is when your speed is low. That gives you the association. Associations are going to be represented graphically by dotted lines between the ellipses for each of the two variables in question. It doesn't go the other way around, though. Just because two variables are associated doesn't mean that one of them has to cause the other. Let's take a hypothetical example to see why this is true. Say that you're looking at a scatter plot here where every little dot represents a mid-sized town in the United States. So maybe there's a couple of hundred towns in this study. And for each town, we've measured two variables. We've measured the number of dogs in the town, and we've measured the number of fire hydrants in the town. These are two numerical variables, so we could study the relationship between them by making a scatter plot. And from the rising cloud of points, we can see that there is certainly a relationship between these two variables. They are associated. Apparently, in towns with a larger number of dogs, there tends to be a large number of fire hydrants. In towns with a small number of dogs, there tends to be a smaller number of fire hydrants. So that's an association if we ever saw one. But does it mean that one of the variables has to cause the other? For example, do we really think that the number of dogs in a town causes the number of hydrants in the town to be what it is, even partially? I mean, do dogs somehow get together and lobby the mayor for more hydrants so they can pee on them? I don't think so. We also don't think that the number of hydrants causes the number of dogs. It's not as if we believe somehow that if dogs hear that a certain town has a very large number of hydrants, that they migrate to that town so they can be around them. What's really going on in this situation is what we call a common cause. It's a third variable that causes each of the two variables under study and produces the association between them. In this case, the common cause could be described as the number of people in the town. That numerical variable causes the number of dogs. Why? Because when more people come to a town, since people tend to own pets, there end up being more dogs in town. But number of people also causes number of hydrants. The more people there are, the more houses there are, and therefore the more city blocks there are, and therefore the more fire hydrants there are on these blocks. This common cause is what produces the association that we saw in the scatter plot between the dogs and the hydrants. Now, a common cause is not the only way to produce an association between two variables. Another very common way of producing an association between two variables, one that makes it very difficult to tell whether either of the two original variables cause one another, is what's called a confounding variable. So again, let's go back to a situation where we have some observed association in our data between some explanatory variable x and some response variable y. And we're wondering how we might explain this association. Certainly one possibility is that x could cause y. And another possibility is that y could cause x. Even if initially we thought of y as the response variable, perhaps a deeper look at the situation might convince us that y is actually the variable that's doing the causing. But there are other possibilities. There could be a third variable, different from x and different from y. This variable z that you see in the green ellipse. And what if that variable is associated with the explanatory variable? Associated with it, but not caused by it. Furthermore, suppose that that third variable helps to cause the response. That is one of the causal factors in the response variable y. Then, z is what we call a confounding variable. The reason is that it's doing some of the causal work on y. Now, x might be doing some of the causal work on y as well. But because X and Z are mixed up together, confounded, associated with one another, it's hard to tell how much of the causal work comes from X, if any at all. Maybe Z is even doing all of the causal work. Before we leave this diagram, I'd like to point out that in the definition of confounding variable, we said that X and Z have to be associated, as represented by this dotted line, but, very carefully I pointed out, that also X must not cause Z. If X did cause Z, then since Z causes Y, X would indirectly cause Y. And what we're looking for is situations where the presence of this third variable makes it impossible for us to say whether X does any causing at all. And so that's why the X does not cause Z is part of our notion of Z being a confounding variable. It's good to look at it entirely verbally as well. So this is our official definition of confounding variable. In a study of the relationship between an explanatory variable X and a response variable Y, the variable Z is called a confounding variable if it's a third variable, different from X, different from Y, if it's associated with X but is not caused by it, and if it helps to cause Y. If all those three things are in place, then Z is a confounding variable. Now, confounding variables are quite often present in observational studies. This is basically because in an observational study, the subjects simply come along with their values for the explanatory value X. They already have them at the time of the study. Maybe they've chosen them for themselves as people choose to smoke or not to smoke. Or maybe they're just stuck with those variables, with those values somehow. For example, when somebody is male or is female. And we all know that smokers and non-smokers probably differ in other ways than just by smoking and non-smoking. For example, smokers probably have different dietary habits than non-smokers, or different exercise patterns, or other different types of lifestyles. And some of these other differences may have an effect on some response variable, such as whether or not someone gets lung cancer. So in observational studies, because the different groups that you compare might differ in some other ways besides the explanatory variable, and those ways, some of them at least, might affect the response variable, you're never sure how much causal work the explanatory variable is doing in the values of the response variable. Let's see an example of how this comes out. Say you have an observational study that finds that brightly colored cars are more likely to receive tickets than cars of more drab colors are. Can we infer that the color of a car is a causal factor in whether or not its driver is going to get a ticket? Well, probably not, because there's a fairly obvious possible confounding variable in the situation, namely the driving habits of the subjects in the study, the drivers. Typically, we think that folks who have speedy driving habits, they like high speed or like adventure, tend to drive cars of brighter colors than those who have very staid driving habits. Maybe this is because the speedier drivers are more likely to purchase sports cars, which tend to have bright and flashy colors. So there's an association between car color and driving habits. I don't think there's a causation in the color to driving habits direction. I don't think that the color of someone's car causes how fast they drive. If I were to change the color of my car from gray to yellow, I don't think it would make me a faster driver or anything. There may be some causal direction going the other way from driving habits to car color, but that wouldn't be a problem for the definition of confounding factor. So we have at least the association and no causation from car color to driving habits. We also pretty clearly believe that driving habits causes whether or not one gets a ticket. The speedier you are, the more likely you are to get a ticket. And so we have what we need to produce that association we see between car color and ticket. If you want to describe why something is a confounding factor, then you need to back up how it meets the conditions in the definition. So one way to do that in this example might be to say, the variable driving habits is a possible confounder. You find a good name for your variable. Then you might go on to say, people who drive fast are more likely than others to prefer sports cars, which are often brightly colored. What you're trying to do is to back up the idea that driving habits and car color are associated. And then finally, you back up the idea that driving habits cause tickets. Their fast driving also causes them to get a lot of tickets. That's a good, tight justification, a good argument for the idea that driving habits is a confounding variable in this observational study. There was a third condition for confounding variable, namely that driving habits is a different variable from car color and from ticket, but that's so obvious, I guess it goes without saying. So if observational studies are pervasively subject to the possibility of confounding factors, so that it's difficult to infer any causation from associations or relationships that you find, then we need to look for another way to design a study so as to make causal inference a little less difficult. And this brings us to the idea of experiments. What's an experiment? In an experiment, researchers manipulate something and observe the effects of the manipulation on a response variable. That's the general definition. But I would immediately say that most commonly this manipulation consists in assigning the values of an explanatory variable x to the subjects. If you want to tell whether something is an experiment, that's the first thing that you should think about. Did the researchers assign the values of the explanatory variable to the subjects? Some experiment terminology that we're going to need right away. The subjects are also called experimental units. They're the individuals who participate in the experiment. It's important to note they don't have to be people. They could be trees or other plants or animals. They could be plots of land. They could be all kinds of things, including fairly abstract objects, all depending on the type of question that you're studying. But they're called subjects or individuals. The treatments are the different values of the explanatory variable that researchers assign to subjects. So the subjects end up being divided into what we call treatment groups, where members of the same treatment group are all going to have the same value for the explanatory value for x. They're all going to have the same treatment. On the other hand, members of two different treatment groups have to have a different treatment because they've been assigned different values of the explanatory variable x. There will be as many treatment groups as there are treatments. Now, here's a question that has to turn out to do with an experiment, that turns out to have to do with an experiment. This was that question about sentences in the attitudes data frame. And we're going to read out here a question on one of the survey forms that students were given. So the question was said to be about crime. You're on a jury for a manslaughter case in Lewiston, Pennsylvania. The defendant has been found guilty, and in Pennsylvania, it's part of the job of the jury to recommend a sentence to the judge. The facts of the case are as follows. The defendant, Tyrone Marcus Watson, a 35-year-old native of Lewiston, was driving under the influence of alcohol on the evening of Tuesday, July 17, 2001. At approximately 11 p.m., Watson drove through a red light, striking a pedestrian, Betsy Brockenheimer, a 20-year-old resident of Lewiston. Brockenheimer was taken unconscious to the hospital and died of her injuries about 1 hour later. Watson did not flee the scene, nor did he resist arrest. The prior police record for Mr. Watson is as follows. 2 minor traffic violations, and 1 previous arrest 5 years ago for driving under the influence of alcohol. No one was hurt in that incident. Watson has now been convicted of DUI and manslaughter. The minimum jail term for this combination of offenses is 2 years. The maximum term is 50 years. In the blank below, students had a blank to fill in, write a number from 2 to 50 as your recommended length of sentence for Tyrone Marcus Watson. So that was the question on one of the survey forms that people filled out. But what no one knew at the time of the survey, no one except the researchers that is, was that not everybody was looking at exactly the same survey form. On all 267 survey forms, the question was the same in all details, except for the names of the defendant and the victim. There were actually 4 different types of forms going around as far as names were concerned. On one form, the defendant was named Tyrone Marcus Watson and the victim was named Betsy Brockenheimer. On another form, the defendant was named Tyrone Marcus Watson and the victim was named Letitia Dawes. On a third form, the defendant was named William Shane Winchester and the victim was named Betsy Brockenheimer. And on a fourth form, the defendant was William Shane Winchester and the victim was Letitia Dawes. These 4 forms, about an equal number of each, were distributed randomly to the students who were in the survey. Now, just looking at the names, you can begin to tell what kind of research question people might have had in mind. No one was really interested in how hard students are on crime. They were interested in whether the race of a defendant or the race of the victim might have some impact on the length of sentence that students would recommend. After all, the name Tyrone Marcus Watson suggests a black male. On the other hand, the name William Shane Winchester, well, that's about as white and country music channel as you can get. Betsy Brockenheimer, that name has kind of a Germanic ring to it and suggests a white person, and Letitia Dawes suggests a black female. So actually, another variable in the study, besides sentence, was def race, defendant's race, and it had the value black or white. Really, the suggested race, black, and the suggested race, white. And another variable in the study was the suggested race of the victim, black or white, and this was denoted Vic race in the attitudes data frame. So a couple of different research questions have emerged. One is whether the suggested race of the defendant affects the length of sentence recommended. And another is whether the suggested race of the victim affects the length of the sentence recommended. In one study, the explanatory variable is def race. In another study, the explanatory variable is Vic race. Now, each of those questions is a question that arises from a study that constituted an experiment. Since the researchers gave the survey form to the subjects, the researchers were assigning the value of def race to each subject, and they were assigning the value of Vic race to each subject. So in both research questions, the values of the explanatory variable were assigned to subjects by researchers, so both questions were studied by means of an experiment. For some practice, think about this research question. Does one's sex affect one's risk of developing colon cancer? Could this research question be studied by an experiment? Now, to answer this question, you have to think about what are the 2 variables at interest here. One variable is sex, male or female, and the other is colon cancer, whether you have it or don't. And the explanatory variable in this case appears to be sex. So we ask ourselves, can researchers assign the values of sex to subjects in a study? And the answer is probably not. People come with the sex that they have. So this time, we can't assign people their sex. So we can't study this question through experiments. We would have to be content with doing observational studies. Now consider this research question. Does taking aspirin help prevent heart disease? Could this research question be studied by an experiment? Well, this time it seems the answer is yes. The explanatory variable is whether or not one takes aspirin. The response variable is whether or not one has heart disease. And focusing in on that explanatory variable, we ask ourselves, could we assign the values of that, yes or no, to subjects? And it seems that we could. If we could get people to agree to a particular regimen, a particular set of rules, so that when they enter the study, they know that they will either be asked to take aspirin every day for some period of time, or they will be asked to refrain from taking any aspirin at all for that period of time. If we could get people to agree to that in advance, then we could make the assignment for each person. And then we could select some of the subjects to take aspirin every day. And the other subjects would have to not use aspirin. Our two treatments, aspirin yes, aspirin no, would form two treatment groups of subjects. The treatment group that takes aspirin every day, the treatment group that does not. Now, why do we go to all the trouble to do experiments? After all, there is some trouble involved. You have to gather subjects who are willing to have variables assigned to them, or you have to do something like what was done in the attitude survey. You have to essentially trick them so that they don't know that they're being assigned different values of some explanatory variable. This can be difficult to do. So why do we undertake experiments? Well, there's a certain ideal that we pursue when we do an experiment that we could never really try to get close to in an observational study. In an experiment, we try to assign the values of X to subjects so that the treatment groups are as similar as possible with respect to every variable that might affect Y, except for the variable X. The different treatment groups will differ in their value of X, but we would like that to be the only difference between the treatment groups. Because if that were so, then any differences in Y that we see between the groups could be ascribed to X and not to some confounding factor. If all the groups are the same with respect to every other variable Z, then there's no way that some other variable Z could be associated with X. And so we couldn't even get started on Z being a confounding factor. So in the next part of the chapter, we'll look at how people design experiments so as to try to approximate this ideal. It can never be achieved exactly in practice, but there are clever ways to approximate it pretty well. Thank you for listening.